Hey guys, how you doing? It's Mr. Lee. Listen, I'm sorry I didn't get to some of these discussion posts earlier, but as you can see, I'm traveling to Europe. I'm in France, Paris right now. Just kidding. Virtual backgrounds are great. But anyways, I wanted to go ahead and address some of these outstanding questions in the chat or in the discussion board, excuse me. So this first one says, hey, Mr. Lee, could you please explain a little more about the density graph used for problems 10 and 11 on page 128? I'm a little confused. It looks like there's just one data point with this big value between 0 and 1, not including 1 because histograms don't include the very right edge. Or is it that every point from 0 to 1, not including 0, occurs only once? So this is quite confusing because this is our first time ever talking about density curves at all. And the most important density curve that we're going to use throughout the course is the density curve that is the standard normal distribution. And so that's why we're spending an entire section of chapter 2 learning about the normal distribution and the properties of the normal distribution, how to do calculations of the normal distribution. So that's the most important thing. But there are a few conceptual questions about, well, what is a density curve and how does it work? Other than the normal distribution, like what are density curves and what are the different shapes and what are some of the different things that you can do with density curves. So a density curve can have any shape, just about any shape. It has to be a curve, and it obviously it never touches the x-axis. It can come really close to touching the x-axis, but it never does. So that's one property. The second property is that the total area below the curve is 1. Okay, and that correlates to the probability of an event occurring. So if you think in terms of probability theory, if you remember what you learned about sample space, the sample space is like every possible outcome that could happen and its associated probability. And the probability of the entire sample space was just a probability of 1, because that is like, you know, everything that could possibly happen. If you think of it not in terms of probability theory, but if you just think of it in terms of proportions, what the book calls proportions, not like an algebraic proportion where one ratio equals another ratio, but a proportion in terms of like the percentage of data, you could say that the area under a density curve contains 100% of all of the data or all of the observations or all of the possible outcomes. Okay, so that's basically what a density curve is. Okay, so this question in the chat or in the discussion board says, and then would you just make a box plot the way we normally would with a 5-number summation? So let me go ahead and show you what the book looks like. So here is the textbook. This is page 128, and this is exercises 10 and 11. So in 10, it says, okay, now we have a uniform distribution. So remember what a uniform distribution looked like? If we're drawing a histogram of a uniform distribution, it would basically look like that, where every outcome has the exact same frequency, okay, or all the data has the exact same frequency. It's kind of like a straight line, okay, and that's a histogram. Now, if instead of a histogram, or if we had like a dot plot, okay, if we had a dot plot, actually we don't, yeah, if we had a dot plot, it would look something like this, right? Just a straight line, horizontal line going across, because everything has basically the same frequency. So now when we're thinking about a uniform distribution for a density curve, or the density curve of a uniform distribution, here's that straight line up top, okay? But the density curve obviously includes the area below it. Now, why does the interval go from 0 to 1 and the height go exactly up to 1? That's because by definition, the area of this entire region, and this is kind of, you can see this kind of a rectangular region, right? So the area of the entire region has to equal 1, okay? And for area, you know, is length times width, right? Area of a rectangle is just length times width. So 1 times 1 is equal to 1. So by mathematical definition, it has to go from 0 to 1 and have a height of 1, okay? Actually, that's not the only combination, but if this is 1, then this also has to be 1, okay? So let's read what it says. Figure 2.8 displays a density curve of a uniform distribution. So that's uniform right there, straight across, right? The curve takes the constant value 1 over the interval from 0 to 1, and 0 and is 0 outside the range of values. This means that the data described by this distribution takes values that are uniformly spread between 0 and 1. So this means, well, how many like possible observations are within this area, within this blue area? There's an infinite number of possible observations. It could be 0.5, 0.25, 0.1, 0.01, 0.001. So there's all these different values that could be could be taken on, but no matter what the value is, it has a frequency of just 1, okay, because this density curve has a height of 1. Okay, so let's look at the actual problems. Okay, so use areas under the density curve to answer the following question. So this is the entire density curve. This is the entire, if you want to use probability language, this is the entire sample, sample space, right? So A, why is the total area under this curve equal to 1? Well, because 1 times 1 gives you 1 square unit, right? So 1 times 1 gives you 1. That's why the area is equal to 1. Okay? What percent of the observations lie above 0.8? So where would 0.8 be, right? If this is some continuous scale, where would 0.8 be? Well, that'd be about 0.5, about 0.75. 0.8 would be somewhere here. So how much of the data, if I were to draw a line, and I'm not going to draw in the textbook as much as I want to, but if I were to draw a vertical line at 0.8, where I think 0.8 is, well, how much of the data lies above or to the right of 0.8? Well, 20% of the data lies to the right of 0.8. Okay, what percent of the observations lie below 0.6? Well, 60% of the data lies below 0.6. What percent of the observations lie between 0.25 and 0.75? 50%, 0.75 minus 0.25. What is the mean mu for this distribution? Well, you can see that it's perfectly symmetric, right? So what would be the mean? Well, the mean is just going to be 0.5. Okay. Number 11, uniform distribution, part 2. I love when they have part 2 to questions. Anyways, part 2. Refer to the previous exercise. Can you construct a modified box plot for the uniform distribution? If so, do it. If not, explain why not. Okay, so forget about modified versus non-modified box plots. There's only one box plot that matters, and that is Mr. Lee's box plot. That is all that matters. Okay? So can we construct a box plot from this data? What would that look like? A box plot of a uniform distribution. Interesting. That one I'm going to leave for further thought. Please answer the discussion board with your thoughts on question number 11. Do you think you could construct a box plot of uniform data? Answer in the discussion board. Thanks, guys. I'm going to move on to the next question.